In this lecture, you'll learn about VMware VVols, that's virtual volumes, with ONTAP storage. A good way to explain and understand VVols is by comparing and contrasting them with traditional data stores. So I'll summarize some of the characteristics of traditional data stores first. Traditional data stores each use one volume if it's NFS, or one LUN in one volume if you're using a SAN protocol on the storage system. Now, I know for the sake of completeness, you can also have data store clusters. A data store cluster is a collection of similar data stores that are aggregated into a single unit of consumption from vSphere's perspective. So a data store cluster is where you group multiple traditional data stores together into one larger storage space. But the traditional data stores that make up that data store cluster are still made up of one volume or one LUN. So when we're talking about traditional data stores, it's one volume or one LUN always that makes up that data store. And ES6i clients use NFS or a SAN protocol, fiber channel, FCOE, or iSCSI to access the data store. With a traditional SAN data store, vSphere formats a LUN with the VMFS file system, and it's vSphere that manages the data in the LUN. vSphere manages the file system, so ONTAP has no visibility of the individual virtual machines and their files inside that LUN. With a traditional NFS data store, ONTAP does have visibility of the virtual machine's VMDK, that's virtual disk files. Because with NFS, it's ONTAP that is managing the file system, so ONTAP can see the files. But with a SAN protocol, it's vSphere that is managing the file system, so ONTAP cannot see the files. So with NFS, a QoS policy within ONTAP can be applied to the entire volume or to individual VMDK files within it because ONTAP can see them. But with SAN protocols and VMFS, an ONTAP QoS policy can be applied to the entire volume or individual LUNs, but not to the files. QoS policies cannot be applied to individual VMDK files because ONTAP has no awareness of the files inside the VMFS file system. So your QoS policies can be more granular if you're using NFS with vSphere than if you're using a SAN protocol. Okay, and that is where really the big benefit and the idea behind VVols comes in. So VVols is an integration, between vSphere and the storage system, and management framework between vSphere and the storage system. It provides granular virtual machine and virtual disk level management to the storage system with both SAN and NFS protocols. So you get that if you're using NFS, but you don't get it normally with traditional data stores if you're using a SAN protocol. It enables policy-based management and compliance monitoring. Now, you saw in the earlier lectures, when you saw the demo with the traditional data store, that there is policy-based management using the storage capability profiles and the VM storage policies. You get that with traditional data stores. But with traditional data stores, that policy-based management is at the volume level if you're using the SAN protocol. It's not at the virtual machine and virtual disk level. So with VVol Datastores, you get that policy-based management at the more granular level, down to the virtual disks that make up the virtual machines. It minimizes manual handoffs between VM and storage admins, so it makes administration easier. And currently, it's VVols version 2.0, which is supported by ONTAP. In fact, before I move on to this slide, I'll just come back here again, because I want to address something now as well. And that is that VVols have famously had a very slow uptake. But a big reason for that is that VVols came out with vSphere version 6. The vSphere version before that, vSphere version 5.5, was a very long-standing, very stable and reliable version. So when version 6 came out, a lot of VMware customers stuck with vSphere version 5.5, which did not support VVols. And because it didn't support it, obviously they could not deploy VVols. So So that's one of the big reasons that VVols is not really in a huge amount of use today. However, having said that, vSphere version 5.5 has now gone end of life, so customers are now moving over to supported versions of vSphere. Also, if you have a look at the technical reports and other documentation that is coming out from NetApp right now, NetApp are pushing VVols quite strongly because you do get the enhanced policy-based management, you do get the extra granularity. Another thing that I'll cover later in this lecture is that there's enhanced offload over and above what you get with VAAI for traditional data stores as well. So VVols do have good benefits. Yes, there's not a huge uptake of them as I'm recording this right now, but that might change going forward. I wouldn't be surprised if you see VVols becoming a lot more popular. Okay, so carrying on, getting into some of the details of VVols. vSphere and the storage system establish a two-way out-of-band communication to manage VVols. The VASA Provider translates between NetApp and vSphere APIs. So the VASA Provider has to be enabled for VVols to be available with your ONTAP storage. When you install VSC, the Virtual Storage Console, VVol Provider is enabled in the latest release of that by default anyway. So a VVol Datastore is a logical storage container construct made up of one or multiple volumes in an SVM on the storage system. So that's a difference there between VVol Datastores and traditional Datastores. A traditional Datastore is always a single volume or a LUN in a volume if you're using a SAN protocol. With a VVol Datastore, it can be a single volume or it can be made up of multiple volumes. Those volumes are, however, always part of the same SVM in the ONTAP storage. So it can span multiple volumes. Those volumes can also be spanned across multiple nodes in the cluster as well, but they do all have to be in the same SVM for the same VVol Datastore. And when you create a VVol Datastore, you specify whether to use SAN or NFS3 as the access protocol. NFS version 4.1 is not currently supported as I'm recording this. All volumes in the same VVol Datastore must use the same access protocol. So if, for example, you're using iSCSI for the Datastore, all of the volumes in that VVol Datastore are going to be accessed by iSCSI. The different ONTAP volumes that make up the VVol Datastore must be in the same SVM, as I said, and use the same access protocol, but they can have different characteristics. For example, one volume in the same VVol Datastore could have deduplication enabled, another volume could have deduplication disabled. And your VSC storage capability profiles, the same ones that you saw when we were using them for the traditional data stores, they define the characteristics of each volume. So when you create your VVol Datastore, you're going to specify how many volumes make up the data store. You're going to specify the size of each volume as well. You're going to specify the access protocol. And for each of the different volumes in there, you can specify different characteristics for the different volumes by using different storage capability profiles on them. Your VVol Datastores are created in the VSC Virtual Storage Console. And when you create a VVol Datastore, you specify the SVM and access protocol. You also specify how many ONTAP volumes will make up that VVol Datastore and the storage capability profile for each one of those volumes. And volumes can be added or removed later. If you wanted to, you could have multiple VVol Datastores in the same cluster if you wanted to. That is supported. When you provision a traditional data store with VSC, you can assign a minimum and maximum traditional QoS IOPS value. Minimum is only supported on AFF, maximum is supported on your fast systems and AFF as well. Adaptive QoS is not supported when you provision a traditional data store with VSC. But both traditional min-max and adaptive QoS are supported when you provision a VVol Datastore with VSC. So that is another benefit of VVol Datastores over your traditional data stores. You can place a virtual machine in a VVol Datastore when the VM is first deployed. You can also migrate a virtual machine from a traditional datastore. So if you've already got a traditional datastore environment, you've got your virtual machines in there, it is easy to just create new VVol Datastores, and then you can then migrate your virtual machines across. Okay, talking about the VVol objects now. So your virtual disks, the VMDK files that make up your virtual machines, also the virtual machine configuration files and other VM files are VVol objects when they are placed on a VVol Datastore. Okay, so when we're talking about VVols, there's really two components there. There's the VVol Datastore, which is made up of volumes on your ONTAP storage, and then there's the VVol objects that go into those data stores. The VVol objects are the files for your virtual machines. They reside directly on the storage system without using a file system. So let's look at the different VVol objects that are going to be created and exist when you deploy a virtual machine onto a VVol Datastore. So separate VVol objects are created for each separate virtual machine, and they're stored as files if you're using NAS or LUNs if you're using SAN. So again, the way that we access our traditional data stores using NFS or a SAN protocol is exactly the same way that you access the VVol data stores. Again, you're going to use NFS or a SAN protocol. If your ESXi hosts are connecting to the VVol data store using NFS, then the VVol objects will be stored as files. If they're connecting with a SAN protocol, then each of the objects will be stored as a separate LUN. So let's look at the different objects. First VVol object, and again, these are for each different virtual machine is going to have these same VVol objects making up that virtual machine. First VVol object is the config VVol. If you're using a SAN protocol, that will be a LUN and it will be 4 GB in size. It is a metadata container for the VMX file, NVRAM, logs, and VMDM descriptors. So the config file contains configuration information about that particular virtual machine. If you're using NFS to access the data store, then it's a directory containing configuration files and pointers to the VM's other VVols. So the config VVol, it's the same thing whether you're using SAN or NAS. If you're using SAN, it will be a LUN. If you're using NFS, it's going to be a directory. Next type of VVol object is the data VVol, and that is the virtual machine's virtual disk, the VMDK file. If you're using SAN, it will be a separate LUN, so a different LUN to the config VVol, and it's going to be the size of the virtual disk. If you're using NFS, then it will be a file, which is the size of the virtual disk. And if you have got, say, 3 VMDK files making up a particular virtual machine, then that is going to be 3 separate data VVols. So if, for example, it was a Windows virtual machine and you've got a C, a D, and an E drive, those are going to be 3 separate VMDK files, which are going to have 3 separate VVol objects. I put a line there on the slide because when you create a virtual machine and you deploy it on a VVol Datastore, you're always going to have the config and the data VVol. The VVols below the line are optional or depending on the actual state of the virtual machine. So first one is the swap VVol, and that's created when the VM is powered on, deleted when the VM is powered off. That is the virtual memory. So it's the swap file, basically. If you're using a SAN protocol, it will be a LUN, which is the size of a virtual memory. If you're using NFS, it will be a file, which is the size of the virtual memory. The next VVol type is memory, and that is created for a virtual machine snapshot. So if you don't have a snapshot, that won't exist. If you do create a snapshot, then that is going to create the memory VVol. In SAN, again, the same as the swap and the data VVols. For SAN, it will be a LUN, the size of the virtual memory. For NFS, it will be a file, the size of virtual memory. You can also have other vendor-specific VVols as well, for example, for data store heartbeats. Okay, so those were the VVol objects that go into the VVol data store. The different VVol objects can be assigned different VM storage policies, which are mapped to different storage capability profiles. So you saw this earlier in the examples for the traditional data stores as well. You saw that we used VSC to provision the traditional data stores on the ONTAP storage, and we used the VSC storage capability profiles to specify the characteristics, such as is fin provisioning enabled or not, on the volumes that were backing the data stores. We then used the vSphere VM storage policies when we were deploying the virtual machines to say what storage characteristics we wanted those virtual machines to get. The VM storage policies were mapped to the storage capability profiles with a one-to-one relationship. So that works exactly the same in VVol Datastores as it does for traditional data stores. The difference is that these policies are not applying at the level of the volume, they apply at the level of the VVol objects. So it's more granular when you use VVols than when you use traditional data stores. Different virtual machines and their files in the same VVol data store can be assigned different service levels. So, for example, maybe you deploy a virtual machine which is being used as a database server, and that database server has got two different virtual disks, two different VMDK files. You could give one of the VMDK files, which is a VVol object, a high performance QoS policy. You could give the other one a lower performance QoS policy. So you've got a lot of granularity with your VVols data store where different virtual disks and virtual machines can be assigned different QoS policies and also other characteristics as well, such as whether they're thin or thick provisioned within the same data store. Not possible to do that with traditional data stores. When you create a VVol data store, you specify the default storage capability profile. This is when you've got multiple volumes making up that VVol data store. Because different volumes can have different storage capability profiles, you're going to specify a default one. The default SCP is used when you create a virtual machine if you do not specify another SCP. So, for example, maybe we create a VVol data store which is made up of two volumes. One is high performance and one is low performance. You would specify the default SCP as the low performance, as the default SCP. It's also used for swap VVols as they do not require high performance. So set the lowest performance SCP as default. So again, I'll summarize that again. Let's say that we've got a VVol data store, which is made up of two volumes. One is high performance and one is low performance. When you provision that VVol data store, you also specify which is the default SCP. You're going to make that the low performance one. Then when you provision a virtual machine and you put it in that VVol data store, the swap VVol is going to get the low performance. And if you don't specify explicitly say for a virtual machine that you want its VMDK file to have higher performance, it will get the lower performance as well. Next, let's look at what happens when you provision a virtual machine. So when you create a virtual machine, its config and data VVols are created at that time. They're both created in volumes in the VVol data store, which you select, which are compatible with the storage capability profile, which you also select. If the virtual machine has multiple VMDK files, a separate data VVol will be created for each one, and different data VVols can be assigned different storage capability profiles. The QoS policy from the selected storage capability profile is applied to each data VVol. No QoS policy is applied to the config VVol. And this makes sense if you think about it. It's the VMDK file, the virtual disk, which is really being used by the virtual machine. That's the one you've got all the I/O going to. The config VVol has just got metadata in there, so performance is not really a consideration for it. When you power on the virtual machine, a swap VVol is created. So when you first create the virtual machine, you've got the config VVol created and also a data VVol for each VMDK. When you power it on, that's when the swap VVol is created. It's created in a volume in the VVol data store, which is compatible with the VVol data store's default storage capability profile. And again, no QoS policy is applied because performance is not a big consideration here again. Next thing to talk about is protocol endpoints. And ESXi hosts do not have direct access to VVols. A logical I/O proxy is used instead, which is called a protocol endpoint. ESXi hosts use the protocol endpoints to establish a data path on demand from virtual machines to those virtual machines' VVols. This provides more scalability because protocol endpoints can service many VVols simultaneously. It overcomes the maximum 256 LUN limitation of the vSphere. So you saw a few slides back, I showed you the different VVol objects that are created for each virtual machine. And if you think about it, if you've got, say, 100 virtual machines on a VVol Datastore, then you're going to very quick, if they were each accessing their LUNs individually, because each of those VVol objects, when you're using SAN, uses a separate LUN. So if for each virtual machine, it's maybe going to have 4 different VVol objects, that is going to be 4 different LUNs. Well, you can see that you would very quickly reach the maximum 256 LUN limitation. It's not like with traditional data stores where it's a single LUN and all the ESXi hosts are connecting in on that single LUN. With the VVol data stores, each separate VVol object is going to have its own LUN when you're using SAN. So a lot of virtual machines, that would be a lot of LUNs. You would quickly reach the scalability limitation. So to prevent you from running into that scalability limitation, the ESXi hosts are not connecting in directly to the individual LUNs. There's a protocol endpoint in front of there, which is used as an I/O proxy. A single protocol endpoint is going to be servicing multiple LUNs behind it. The VASA provider creates the protocol endpoints on the ONTAP system when a VVol Datastore is created. For NFS, a protocol endpoint is created for each NFS LIF in the SVM, and for SAN, a protocol endpoint LUN, which is 4 megabytes in size, is created in each volume in the VVol Datastore. So you'll see this when I do the lab later, that when I provision the VVol Datastore using a SAN protocol, the 4 meg protocol endpoint LUNs are going to show up in the LUNs page in System Manager. The VASA provider controls the data paths and the multipathing. Okay, next thing is the enhanced offload operations that I spoke about right at the start of the lecture. So as we've been going through the rest of the lecture, you've seen that big benefit of VVols is that additional granularity that you get, especially with your SAN protocols. It allows you to set characteristics of the storage for your virtual machines at the virtual machine and even down to the virtual disk level. And different virtual disks for your virtual machines, even in the same VVol Datastore, can have different performance characteristics set on them. So you get that additional granularity. The other benefit that you get with your VVol Datastores is enhanced offload operations. So the VASA provider for VVols provides enhanced offload operations above what is supported by VAAI for traditional data stores. The things that it supports are native ONTAP snapshots when a snapshot is created in vSphere. With traditional data stores, the snapshots will be offloaded for linked clones, but just standard VMware snapshots are not. But with a VVol Datastore, your standard VMware snapshot, that is going to be offloaded to become a NetApp snapshot, which is more efficient. Also, offloaded NFS storage vMotion while your virtual machines are powered on. That is supported in traditional NFS data stores while VMs are powered off, but not when they're on. With VVol Datastores, you get offloaded storage vMotion when they're powered on as well. Also, continuous access of virtual disks moving or being copied to a new volume. So if you do move a virtual disk in a VVol Datastore to a new volume, your clients can still access the disk continuously while that is occurring. Also, during restores, you get the continuous access there as well. Okay, so that was everything. Final slide is to tell you about OnCommand API Services. The VASA dashboard and reports provide data store and virtual machine level capacity and performance information. You must register OnCommand API Services with the VASA provider to enable them. Okay, so to provision a VVol Datastore and for your ESXi hosts to use it, you need to have VSC installed and you need to have the VASA provider enabled. Okay, that's just to provision and use the VVol Datastores. You do not need to have OnCommand API Services installed to provision your VVol Datastores. What you do need to have OnCommand API Services installed for is to see the VASA dashboard and reports. So you'll be able to provision VVol Datastores without it, but then you won't be able to see the performance and the capacity, etc. information, the dashboard and reports. So to see the dashboard and reports, you also need to install OnCommand API Services. That is separate downloadable software from the NetApp website, and that gets installed separately on a Linux host, which is probably going to be inside your VMware environment running as a virtual machine. Thanks for watching. If you want to get hands-on practice with NetApp storage for free on your laptop, then you can download my free ebook, which you can see above my head right now. Also, check out my NetApp Storage Complete course, which will teach you everything you could possibly want to know about ONTAP. Thanks.